Hi everyone, how's it going? Today we are going to solve one example about chapter 5, which was about serviceability and deflection. And we will see how to use the procedure that I talked about for finding short-term and long-term deflection for an example that is shown over here. It is very important to solve this example. So I'm going to leave some time at the end of this session for you to repeat solving it at home. And if you face any question, I'm available online through WebEx. Just send me an email and we can quickly switch to WebEx and discuss that. Or if it is just a question, send me an email and I can answer your question through email. The example, you can see it is shown over here. In this example, some information is given to us. As you can see, the cross section is given to us. We have a rectangular shape as the cross section of the beam, and also a simply supported beam is considered as the member that we are going to calculate the deflection for. As you can see, the question is asking us to calculate instantaneous or immediate and long-term deflection for the shown beam below, assuming 30% of the live load is applied over 4 years. Live load is given to us as 1.6 kip per foot. Dead load is given to us as 2.4 kip per foot. F prime C, Fy, the properties of material are also given to us. Dead load is not specifying whether the self-weight is included or not in the material or in the loading. So the default assumption that we have in this course is that whenever dead load is given to us without any specific information about whether the self-weight is included or not, we can assume this number is including the self-weight. If the self-weight is not included, I will specify it in the question. I will say self-weight is not included in the given dead load. So this dead load is including self-weight of the beam. As you can see, the information are listed, and what we need to do is to just follow the procedure that we had in the presentation file or in the sessions that we described last time. And based on these 6 steps that we talked about in slide 38, we can calculate the short-term or immediate and long-term deflections. At first, we have to find the immediate deflection due to dead load. Then, as I said, because of the sequence of loading, we always have live load on the dead load. We never have live load alone. That's why if we want to find the deflection due to live load, we have to consider deflection due to dead and live together and then subtract the deflection because of dead load. As you can see, these are the 3 steps. The first 3 steps, which are about finding the deflection because of live load. And then we have the immediate or instantaneous deflection because of sustained load, the load that is going to be applied over years. In some questions, it specifies, for example, a percentage of live load is going to be applied over, for example, 2 years, 3 years, or 4 years. And in that situation, we have to consider the remaining 3 steps, or steps 4, 5, and 6, for finding the long-term deflection. The idea is the same. We always have the dead load over there because that is majorly the self-weight of the material. So all the deflections that we are calculating should be based on additional loads on the dead load. And then if we want to know the deflection because of those specific additional loads, we have to remove the deflection because of dead load to find that secondary deflection. And finally, in the last step, we have the specific equation for long-term deflection. We talked about it in the in the examples that we solve at the end of this chapter, and we are going to use it again in the example that we are going to solve right now. The thing that I believe I forgot to mention in this example is the length, and that is 30 feet. The length of the beam is 30 feet. Of course, you can see it later in the solution, but I should have mentioned it in the question statement. But length of this beam is equal to 30 feet, and I will fix it once I post the example. So now all we need to do is to just follow the steps that I described earlier. First, we have to find the deflection because of dead load. We have a simply supported beam, and as you remember, based on the diagrams that I showed you in the previous sessions, we have these equations for famous forms of loading and beams. Like, for example, for simply supported beam under uniformly distributed load, we have this equation, 5WL to the power 4 divided by 384 EI. And then for other situations, whether we have different boundary conditions, like for example, fixed, or cantilever beam, or point loads, we have different forms of equation. And if you are facing a situation that is not mentioned over here, you can simply look at the structural analysis books, or even you can Google the type of loading and beam, and you can find the structural analysis table, and simply you can find the equation for that deflection in the beam. So over here we have a simply supported beam. I know maximum deflections happens in the middle of the beam, and the equation for finding that deflection is equal to 5WL to the power 4 divided by 384 EI. W that we have over here is the dead load, and as you can see, I'm not including any load factor over here, and this is the rule whenever we are looking at serviceability limit state. As you remember, we had ultimate strength limit state and serviceability limit state. Whenever we are checking or calculating the serviceability limit state values or equations, we never include the load combinations and load factors. We can simply just add the loads together or consider loads alone without including any load factor. In the third chapter, when I was talking about the load factors, I said we are talking about ultimate strength limit state, and over there we want to consider all the uncertainties in loading, and we want to see if the ultimate strength of the section is enough carry all the loads. That's why we included the load factors and load combinations for ultimate strength limit state. In this chapter and example, we are looking at serviceability. It is deflections, and whenever we are dealing with deflections and serviceability questions, we don't include load factors. It's just the values of loads without inclusion any load factor or any of those load combinations that we looked at before. So the dead load is over here as the distributed load, that is equal to 2.4 kip per foot. I'm putting that over there. L is equal to 30 feet. I included this in the equation, in the question. 384 is just the factor in the equation. E is the Young modulus of concrete. We know the equation for that. And I is the effective moment of inertia, and that is the important thing that we talked about in this chapter. I have to see this table based on the very recent and last version of ACI code, and as you remember, I specified the equation for that, and as you can see, it is mentioned over here in slide 28. This is the table that we need to use for finding effective moment of inertia. In the recent version, in the 2019, it is saying that if the applied moment or the moment that you are considering is smaller than 2/3 of cracking moment, you have to consider gross section properties. And if the applied moment is greater than 2/3 of the cracking moment, we have to consider this equation, which is brand new in this version of the code, for finding the effective moment of inertia. So considering this table and this equation, I have to calculate the cracking moment and compare the moment because of dead load versus 2/3 of cracking moment and see what is the situation. The cracking moment is the same thing that we calculated in chapter 2. So the same idea is applied, the same equation. Fr is the tensile strength of concrete, the equation that we used for chapter 2 when we were looking at the stages of concrete behavior, whether it is cracked or not. So Fr is 7.5 square root of F prime C. F prime C is given as 4,000 psi. Ig is the gross section moment of inertia. Gross section is just the concrete section. And as you can see, that is 16/24. So that is the gross section moment of inertia. And then Yt is the distance from centroid of the gross section to the tensile portion, which is just 24 divided by 2. Putting everything in this equation, the final value is 728,000 pound an inch. Changing it to cube foot, it's about 60 cube foot. So I have to compare the applied moment, which in this case is the moment because of dead load, and that was 270. That is definitely greater than 2/3 of the cracking moment. So I have to use this equation that is given to us in the HCI code for finding the effective moment of inertia. The equation is shown over here. It is I crack or cracked section, or we can also say transformed section, moment of inertia divided by 1 minus this parenthesis to the power 2 multiplied by the second parenthesis. The first one is 2/3 of cracking moment versus or over MA, and the second is just 1 minus cracking moment of inertia or cracked section moment of inertia over gross section moment of inertia. In this equation, we have the cracking moment, we have the applied moment or MA, which is 270. What we don't have is the cracked section moment of inertia, ICR. For finding that, I have to consider this transformed section. The section has cracked, so concrete in the tensile region is removed. We have to consider the transformed area of steel because it is a composite section. And this is the approach that we learned in the strength of materials for finding the neutral axis in composite sections, in sections that are constructed based on different materials. D is the distance from very top of the section to the centroid of tensile reinforcement, and D prime is the distance from top of the section to the centroid of compression reinforcement, and Y bar is the distance of neutral axis, which I have to find based on definition of neutral axis. At first, I need to know the transformed area of steel, that is N multiplied by A prime S, area of compression reinforcement, or N multiplied by AS, area of tensile reinforcement. N, as we talked about earlier, is the ratio of Young modulus of steel over Young modulus of concrete. Young modulus of steel is the number that is known, and it's the same thing for all grades of steel, 2.9 multiplied by 10 to the power 7 psi. And EC is Young modulus of concrete, which is based on the ACI suggested equation. That is 57,000 square root of F prime C, which is 4,000 psi. Calculating this, as I said earlier, it should be about 7, 8, 9, something in this region. But in this case, it is 8. So I know the moment area of different parts in the section about neutral axis should be equal to 0 when we add them together. So that is the major equation that we use for finding the location of neutral axis. On one side, I have just the steel. So that is N multiplied by AS and then multiplied by its distance from the neutral axis, which is D minus Y bar. And on the other side of neutral axis, I have this block of concrete. And I also have this transformed area of compression reinforcement. For the compression reinforcement, we have NAS prime and then multiplied by a distance from its centroid to the neutral axis, which is Y bar minus D prime. As you can see, it is mentioned over here. It is mentioned over here. And for the compression concrete that I have over here, this compression concrete, the area is equal to B. This is B multiplied by Y bar. And then the distance is just centroid of this concrete block, which is Y bar over 2, which is mentioned over here. So area multiplied by the distance from centroid of the area to the neutral axis. This is the equation that we need to solve for finding Y bar or the depth of neutral axis or the location of neutral axis in the transform section. So solving this equation, you can put it in your calculator. That's the thing that I do. I simply put it in my calculator and find Y bar. Or if you simplify this equation, it will be this equation, it will be a parabolic equation, and all you need to do is to just calculate it based on the calculus knowledge that we have. As you remember, we said if we have an equation like this, ax squared plus bx plus c equal to 0, x1 and x2 can be calculated based on the equation that we had, and that was I believe minus b plus and minus the square root of b2 minus 4ac divided by 2a. Whether it is plus or minus, we can get one of these roots. But that is something from calculus. I just wanted to remind you about that if you are not using your calculator for finding the roots of this equation. But once you solve it, you can see you get two values for Y bar. One of them is negative, which is meaningless. The second one is the useful value for us, and that is 7.6 inches. Now that I know the depth of neutral axis or Y bar in the transform section, I can find the moment of inertia of this transform section that we have over here. ITR or ICR, you can use both of them. We are basically referring to the same thing. That is the moment of inertia of this section. At first, I have this concrete block over here, and I want to calculate the moment of inertia about this bottom line. So that is B Y bar cubed over 3. It is over 3 because I'm calculating it about the bottom line of the section. So B Y bar cubed over 3 plus the moment of inertia because of this steel over here. That is the area multiplied by the distance to the power 2. As you can see, the distance is equal to D minus Y bar. That will be this distance over here. And then we have the moment of inertia because of compression reinforcement area, which is NAS prime, multiplied by the distance, which is Y bar minus D prime, which will be distance, this distance. Putting all the values in the equation, you can see I put all the values in the parameters that I described earlier. You can see the effect, the cracked section moment of inertia is equal to 10,055 inch squared. Comparing it versus the gross section moment of inertia, we can see that the value has dropped a lot. The gross section moment of inertia, I calculated the value over here. The value is not mentioned, I didn't mention it, but if I want to give you the value, that is equal to 18,000 and approximately 400. So that is the IG. And as you can see, when the section cracked, the moment of inertia dropped from 18,400 to 10,055, about 10,000. That is how the section properties will change when concrete section cracks. So now we can return to this equation that we had earlier, put everything in this equation and find effective moment of inertia, right? So I put everything in the equation. Note that we are calculating the effective moment of inertia just under the dead load. As you can see, this equation is a function of applied moment. And since right now we are looking at the deflection because of dead load, the moment that we are putting over here is the moment because of dead load. We calculated it over here, right? So putting that in the equation, over here, everything else is calculated already. So calculating this equation, final value is equal to 10,156 inch to the power 4. Now that we have this value, I can find the deflection because of dead load, and that is basically using the equation that we talked about earlier. Now that we have the effective moment of inertia, I can put it in the equation, and that is over here, and we can find the deflection. Note that for the loading or WD, I changed it from kip foot to pound inch. The load is equal to 2.4 kip per foot. But since the Young modulus that we have for concrete is in pound inch, this is calculated based on this equation, and that is PSI, pound per square inch. That is why I changed the loading also to pound inch, and also the length that we have is 30 feet. So I multiplied it by 12 to change it into inches because I want all the numbers in the equation to be in the same units. So calculating this, we can see the deflection because of dead load is 1.19 inches. That is the immediate deflection or instantaneous deflection because of dead load. Now I have to find the instantaneous or immediate deflection because of dead and live load together. So the applied moment will be dead and live together. I have to just add the live load to the dead load. And as you can see, that will be 4 kip per foot, multiplying it by the length, dividing it by 8. That is just the maximum moment in simply supported beams. The moment is equal to 450 kip per foot. So the moment has changed, which means the effective moment of inertia when dead and live loads are applied together should be also updated. As you can see, the equation is the same. The only thing that I need to update, I'm showing it in red, is the applied moment. I put this value over here in the equation and then calculating the value. Since the moment is increased, you can see the effective moment of inertia has decreased when we compare it versus the effective moment of inertia when it was just because of dead load. So looking at these values, you can see the applied moment increased, and that's why the effective moment of inertia has decreased. That is something that at least I always check when I'm solving problems to see if values are really reasonable or not. So I find the effective moment of inertia because of dead and live load, and now all I need to do is to just calculate the deflection because of dead and live by putting the live load in the top of the ratio and the effective moment of inertia in the bottom of ratio. The equation is the same. Deflection in simply supported beams because of distributed load. The only things that I changed is the loading and also the effective moment of inertia. Calculating this, we can see the instantaneous or immediate deflection because of dead and live load together is equal to 2 inches. So now I can calculate the immediate deflection because of live load by subtracting the immediate deflection because of dead load from this value that is shown over here, and then you can see the remaining is equal to 0.81 inches, and that is the immediate deflection because of live load. Now that we have this value, I can answer one of the questions. It said calculate instantaneous and long-term deflection. So far we could calculate the instantaneous deflections, dead load, live load, and now I can look at the long-term deflection, assuming 30% of the live load is applied over 4 years. So now I have to find the instantaneous or immediate deflection because of sustained load, which was only 30% of the live load. For that, I have to first include that additional load into the dead load. Then I have to find the deflection because of that. Then I have to subtract the deflection because of dead load to find the deflection just because of the sustained load, and then put it in the equation for long-term loads or long-term deflections. And by including the long-term factors, we can find the long-term deflection. So calculating the moment because of dead and sustained load, again, it is the same equation that we used before. The only thing is that I am adding the sustained live load to the loading. Dead load is the same. The moment is equal to 324 kip-foot. Then the same equation for effective moment of inertia. The only thing that is changing is the applied moment. Over here it is dead and sustained live load. And as we calculated before, that is 324. So put it over here. You can see that the effective moment of inertia will be 10,124 inch to the power 4. Now I have to just use this effective moment of inertia in the equation for deflection, and also the loading should be updated based on the sustained live load. Putting the loading and also the effective moment of inertia, we can see the deflection because of dead and sustained live load is equal to 1.44 inches. Now if I want to know the deflection just because of sustained live load, I have to subtract the deflection because of dead load, and that will be the value for me to find the long-term deflection. The equation for long-term deflection is the thing we described in the presentation. As you remember, over here I showed you the equation. This is the equation that we need to use. Long-term deflection is equal to immediate deflection because of live load plus the long-term deflection factor, or lambda infinity, multiplied by immediate deflection because of dead load. This is lambda infinity because dead load is going to be there forever. It is not going to change. So that is why we have lambda infinity for this, and then lambda t, the factor specifically for the time period that is mentioned in the question, multiplied by sustained live load. Considering that, I have to just use this equation in this example. You can see the equation is mentioned. The only thing is that lambda t is now based on 4 years that is specified in the question. So lambda t is the equation that we had based on ACI code. We talked about it over here. As you can see, this is the equation, and this is part of the ACI that is talking about it. It is based on psi over 1 plus 50 rho prime. Rho prime is based on compression reinforcement. We will see how to calculate it. Psi is the time dependent factor. And as you can see, based on either this table or this graph, we can find the value of psi. So at first, I'm going to calculate lambda infinity. That is psi infinity, or the maximum value for psi. As you can see, this is 2, or if you see this graph, it is converging to 2 when we go to infinity. So psi infinity is equal to 2, and then 1 plus 50 rho prime. If we go back and look at the cross section, you can see compression reinforcement are 2 number 9 bars, and area of each number 9 I believe is equal to 1 inch squared. So 2 multiplied by 1 divided by BD, which is 16 by 21. And then we can see lambda infinity is equal to 1.54. And that is a factor that I need to consider over here. Then I have to calculate lambda for 4 years. So psi should be psi for 4 years. If I go back and look at this graph, 4 years is 48 months. And that is some value over here. As you can see, it is very close to 2. Let's say 1.9. And then 1 plus 50 rho prime is the same that we calculated earlier. Calculating this, we can see the factor is equal to 1.46, and that is the value that I can use in the equation. So lambda 4 years is equal to 1.46. And now I have to just put this in this equation that we had for long-term deflection. Immediate deflection because of live load was already calculated. Lambda infinity is over here. Immediate deflection because of dead load was this much. Then we have lambda for 4 years, that is 1.46. And then immediate deflection because of sustained load is the value that we found in the last deflection calculation. Putting everything in the equation, we can see the long-term deflection is equal to 3 inches. So we could find the long-term deflection, but there are some things that I want you to notice specifically about this example, and that is the comparison between the strength versus the deflections that we are seeing in the solution. The example or the question problem is not asking about the strength of the section. As you can see, it is just talking about the deflection values. But one thing that you can do as kind of extra effort or bonus work is to look at the strength of the section, or phi mn, and compare it versus mu. By this comparison, you can see at some amount of loading, we are seeing such long-term, or let's say, for example, short-term deflections. You might see that phi mn is smaller than mu, which means section has failed. And then that will be an interesting thing to see what is the theoretical calculation values when the section has already failed under some loading. That is one thing that you can do. The other thing that I suggest you to do is to remove the compression reinforcement and then solve the problem again. Remove the compression reinforcement, or these 2 number 9 bars. Of course, it will be very similar to what we solved in the class, but in terms of comparison of deflection values, that will be a good thing to see. Removal of this compression reinforcement, how influences the deflection values. And then you can also remove this compression reinforcement and calculate phi mn and see how does this removal change the strength and also change the deflection values. That will be an interesting thing to study next to the major thing that we studied in this example. I'm going to leave the remaining of the time for you to solve this important example at home. If you want, we can also talk about this additional note that we have over here to see what is the situation. But the thing that I want from you is to see how we have to find the deflections for double reinforced sections. And if you have any question, just let me know and we can discuss it in the WebEx meeting. Thank you.